Please pause the video and try this problem. Now let's discuss the problem together. Here's a summary of the solution for part A of the problem. Now let's discuss the solution step by step. After it's hit and before it hits the ground, the only force on the golf ball will be the force of the Earth's gravity. So the ball will undergo projectile motion. The golf ball's parabolic path of motion was already drawn for us. The problem tells us that the golf ball reaches a vertical height of 25 meters and that it travels a total horizontal distance of 215 meters before it hits the ground. Build that information into the sketch, like so. Write down the key points in time in your sketch. Let's call the instant when the golf ball is hit t sub 0. T sub 0 is the instant when the golf ball begins to undergo projectile motion. Let's call the instant when the ball reaches the peak of its trajectory t sub 1. T sub 1 is a key point in time for this problem because the problem tells us the ball's height at that point in time. Let's call the instant when the ball hits the ground t sub 2. T sub 2 is the instant when the ball stops undergoing projectile motion. T sub 2 is a key point in time for this problem because the problem tells us the horizontal distance that the ball travels between t sub 0 and t sub 2. Let's choose up and right as our axes for this problem. This location is the furthest left position of the ball during the interval of projectile motion and the furthest down position of the ball during the interval of projectile motion. So let's choose this position as the origin. Write down the coordinates for position for each of the key points in time in your sketch, like so. When possible, write down a specific value for each coordinate, like so. Projectile motion is symmetric. That means that the horizontal distance that the object travels as it moves from the ground up to the peak must equal the horizontal distance that the object travels as it moves from the peak back down to the ground. That means that the horizontal distance that the golf ball travels between time 0 and time 1 must equal the horizontal distance that the golf ball travels between time 1 and time 2. That means that the distance from here to here must be half of 215 meters. So this distance is 107.5 meters, and this distance is also 107.5 meters. This tells us that x1 equals 107.5 meters. Remember, when you figure out new information, build that information into your sketch. Identify the question. Part A asks us for the initial speed and direction with which the golf ball is hit. The speed represents the magnitude of the velocity vector, and the golf ball's direction of motion represents the direction of the velocity vector. So, Part A is asking us to find the magnitude and direction of the velocity vector at time 0. Let's build that question into the sketch. The velocity vector at time 0 is drawn tangent to the object's path of motion at time 0. Tangent to the path of motion at time 0, like so. Part A asks us for the magnitude of the velocity vector at time 0. We can represent that question with the symbol v sub naught, written without an arrow on top, to indicate that the symbol stands specifically for the magnitude of the velocity. Part A also asks us for the direction of the velocity vector at time 0. We can represent the direction of the velocity vector with the angle theta, which is formed at the tail of the velocity vector. You can see that we've built the question for Part A into the sketch. And we've represented what the question is asking us for with two symbols. The The problem doesn't tell us the golf ball's velocity at any particular point in time, so for this problem there's no need to go through the process of breaking a velocity vector into components. In projectile motion, the vertical velocity at the peak of the trajectory is 0. Here's why. If an object changes its direction of motion in a component at a particular point in time, then the velocity in that component at that particular point in time is 0. Well, in projectile motion, the object changes its direction of motion in the vertical component at the peak of the trajectory. So, in projectile motion, the vertical velocity at the peak of the trajectory is 0. Since we're treating the peak of the trajectory as one of the key points in time for this problem, we should build this information about the vertical velocity into the sketch, like so. The initial and final points are defined as the 2 points that we plan to substitute into our kinematics equations. The question for part A is asking us about the velocity at time 0. So we plan to substitute time 0 into the kinematics equations. So we label time 0 as our initial point. Should we label t sub 1 at the peak of the trajectory as our final point? Or should we label t sub 2 when the ball hits the ground as our final point? Well, we know the vertical velocity at t sub 1, but we don't know the vertical velocity at t sub 2. Since we know more about t sub 1 than we know about t sub 2, it will be more helpful to substitute t sub 1 into our kinematics equations than to substitute t sub 2. So we plan to substitute t sub 1, not t sub 2, into our kinematics equations. So we label t sub 1 at the peak of the trajectory as our final point. For each projectile motion problem, you choose which 2 points you want to treat as your initial and final points. Don't assume that you should always choose the beginning and end of the projectile motion path as your initial and final points. Always be careful to label the points you choose as your initial and final points with an I and an F. Now we write down the projectile motion setup, and then we work with the kinematics equations. Let's begin our projectile motion setup like so. Part A is asking us about the magnitude and direction of the overall velocity vector at time 0. None of the kinematics variables in our setup will directly answer that question, so I won't label any of these kinematics variables with a question mark. In order to determine the overall velocity vector at time 0, we will need to figure out the components of the velocity vector at time 0. That means that v sub x and v initial y are the kinematics variables that we need to figure out in order to answer the question. So I will label v sub x and v initial y with the word need. For v initial y, we can use the more specific symbol v sub 0y. For v sub x, I will continue to use the symbol v sub x. Substitute specific numbers or symbols into your projectile motion setup, like so. For delta t, let's use the more specific symbol delta t sub 01. This symbol stands for the time that elapses between t sub 0 and t sub 1. We still have 2 unknowns in our x equation, so we're not ready yet to solve the x equation. When you know values for 4 of the variables in your setup for the y component, you're ready to choose a kinematics equation for the y component. We do know 4 values for the y component: y initial, y final, v final y, and a sub y. So we are ready to choose a kinematics equation for the y component. Which kinematics equation should we choose? Well, we don't know the values yet for delta t or for v initial y. So we don't want to choose an equation that includes both delta t and v initial y, because then our equation would have two unknowns. So we need to choose an equation that's missing delta t, or we need to choose an equation that's missing v initial y. None of these three equations is missing v initial y, but this equation is missing delta t. So this is the equation that we need to choose. First, write the general equation. V final y squared equals v initial y squared plus 2a sub y times y final minus y initial. Next, we use our kinematics setup to substitute specifics into the equation. Our kinematics equation now has one unknown, so we can solve this equation for v sub 0 y. To get rid of this exponent, we will need to take the square root of both sides of the equation. Now, any positive number has both a positive square root and a negative square root. Should we take the positive square root of 490, or should we take the negative square root of 490? Well, we expect that at time 0, the golf ball's vertical motion will be upward. Up is our positive y direction, so we expect v sub 0 y to be positive. So we need to take the positive square root of 490. Our result is that v sub 0 y equals positive 22.1 meters per second. Let's build our result for v sub 0 y back into our projectile motion setup, like so. We still need to determine v sub x. Before we can find v sub x, we will need to determine delta t. So our plan is to use our setup for the y component to determine delta t. Then we can substitute our result for delta t into the kinematics equation for the x component. Then we can use the equation for the x component to find v sub x. We now know values for all of the kinematics variables for the y component except delta t. So we can use any kinematics equation for the y component that includes the variable delta t. This equation and this equation both include delta t. This equation is missing delta t, so we won't use this equation at this point. This equation is simpler, so let's use this equation. First, we write the general equation. Then we can use our projectile motion setup to substitute specifics into the equation. Notice that we're making use of our previous result that v sub 0 y equals positive 22.1 meters per second. Now we can solve this equation for delta t. Our result is that delta t equals 2.255 seconds. Now we substitute our result for delta t, which we obtained from our work on the y component, into the kinematics equation for the x component. Our x equation now has only one unknown. So we're ready now to solve this equation for v sub x. Our result is that v sub x equals positive 47.7 meters per second. Now let's build our results into the sketch. We've determined that the time that elapses between time 0 and time 1 is 2.255 seconds. We can build that information into the sketch here and here. We've determined that v sub x is positive 47.7 meters per second, and v sub 0 y is positive 22.1 meters per second. We can build that information into the sketch here. In projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. So, we can also build our result for v sub x into the sketch at time t sub 1, like so. So far, we've determined the components of the velocity at time 0, but Part A is asking us to find the magnitude and direction of the overall velocity vector at time 0. So now we need to use the components of the velocity at time 0 to determine the magnitude and direction of the overall velocity vector at time 0. First, we draw a right triangle in which the hypotenuse represents the overall velocity vector at time 0, and the legs represent the components. We can use the Pythagorean theorem to determine the magnitude of the overall velocity vector. Our result is that the magnitude of the overall velocity vector at time 0 equals 52.6 meters per second. Let's build this new piece of information back into our triangle. Now, how do we determine the direction of the overall velocity vector? The direction of the overall velocity vector can be described by the angle, which is formed at the tail of the overall vector. We've labeled that angle with the symbol theta. To find theta, we'll need to use one of the SOHCAHTOA equations. First, I label angle theta with an asterisk to indicate that I plan to use this angle, theta, at the tail of the overall vector in my SOHCAHTOA equation, rather than using this angle at the head of the vector in the SOHCAHTOA equation. I label this side as hypotenuse because it's across from the 90-degree angle. I label this leg as adjacent because it's adjacent to the angle we marked with the asterisk. And I label this leg as opposite because it's opposite from the angle we marked with the asterisk. At this point, we know the lengths of all three sides of the right triangle. So we could use the equation for sine, or for cosine, or for tangent. In this situation, the conventional approach is to use the equation for tangent. First, write the general equation. TOA, tangent equals opposite over adjacent. Now we substitute specifics. The length of the opposite leg represents the magnitude of v sub 0 y, which we know is 22.1 meters per second. The length of the adjacent leg represents the magnitude of v sub x, which we know is 47.7 meters per second. Now, we're trying to solve this equation for the variable theta. In this version of the equation, the angle theta is inside the tangent function. In order to solve the equation for theta, we need to rewrite the equation so that theta is no longer inside the tangent function. We can rewrite the equation like this. You can see that the equation is now solved for theta. This equation is read theta equals the inverse tangent of 0.463. I can calculate the inverse tangent of 0.463 on my calculator. Notice that on this calculator, the inverse tangent symbol is written in blue, above the tangent key. That means that the inverse tangent function on this calculator is accessed by using the blue second key. So I hit the second key, then I hit this key to access the inverse tangent function, and now we take the inverse tangent of 0.463. Our result is that theta equals 24.8 degrees. Now we're ready to answer the question for part A. Our answer is that the golf ball is hit with an initial speed of 53 meters per second and an initial direction at an angle of 25 degrees above the horizontal. Now we work on part B of the problem. Here's a summary of the solution for part B, and now let's discuss this part of the solution. These question marks represent the question for part A. So now we can build our answers for part A into our main sketch, and then we can erase these two question marks. Identify what the question for part B is asking you for. Part B asks, how long was the ball in the air? When possible, build the question into the sketch. When possible, represent what the question is asking you for with a symbol. The ball is hit into the air at t sub 0. and the ball hits the ground at t sub 2. So part B is asking us for the time that elapses between t sub 0 and t sub 2. We can build that question into the sketch like so. And we can represent what the question is asking us for with the symbol delta t sub 0, 2. This symbol stands for the time that elapses between t sub 0 and t sub 2. I'll bet a lot of students would fall into the trap of saying that the answer for part B is 2.255 seconds. Notice that you can avoid that type of trap by making it a habit to build the question into the sketch. Projectile motion is symmetric. That means that the time it takes for the ball to rise from the ground to the peak will be the same as the time it takes for the ball to fall back down from the peak to the ground. In part A, we figured out that it takes 2.255 seconds for the golf ball to rise from the ground to the peak. So now we know that it also takes 2.255 seconds for the golf ball to fall from the peak back down to the ground. Build that new piece of information into your sketch, like so. It should be obvious now that the total time that elapses between t sub 0 and t sub 2 is 2.255 seconds plus 2.255 seconds, which equals 4.51 seconds. Now we can answer the question for part B. Our answer is that the ball was in the air for 4.5 seconds. Now let's discuss part C. If you originally had trouble with part C, now would be a good time to pause the video and try part C again. Okay, now let's discuss the solution for part C. This question mark represents the question for part B, so we can erase this now. Let's identify the question for part C. Part C asks, what's the smallest value of the ball's speed over its entire trajectory? When possible, represent what the question is asking you for with a symbol, or in this case, with a combination of a word and a symbol. The speed represents the magnitude of the velocity vector. We can represent the magnitude of the velocity with the symbol v, written without an arrow on top. To answer part C, we need to think in terms of components. In projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. Since the horizontal speed is constant, the smallest overall speed will occur when the ball experiences its smallest vertical speed. So, to answer part C, we have to ask, what is the smallest value of the ball's vertical speed over its trajectory? As we've discussed, in projectile motion, the vertical velocity at the peak is 0. So during its projectile motion, the ball's smallest vertical speed will occur at t sub 1, at the peak of the trajectory. At t sub 1, the vertical speed will be 0, as we've already written here. So at t sub 1, the overall speed will equal the horizontal speed. The horizontal speed throughout the projectile motion is 47.7 meters per second, as we've written here and here. So, the ball's smallest speed occurs at t sub 1, when the vertical speed is 0, and the overall speed equals the horizontal speed. At t sub 1, the overall speed will equal 47.7 meters per second. So our answer for part C is that the smallest value of the ball's speed over its whole trajectory is 48 meters per second. Now let me ask you a question. Did you get part C correct? If you got part C correct, excellent. If you did not get part C correct, that means that you need to make a stronger effort to think in terms of components. The key to getting part C correct was thinking separately about the horizontal component of the velocity and the vertical component of the velocity. To give you a little more intuition for this result, remember that projectile motion is symmetric. So the vertical speed when the ball hits the ground will be the same as the vertical speed when the ball leaves the ground. So v sub 2y equals negative 22.1 meters per second. And the overall speed when the ball hits the ground will be the same as the overall speed when the ball leaves the ground. So, the magnitude of the overall velocity vector at t sub 2 equals 52.6 meters per second. So, the ball leaves the ground with a vertical speed of 22.1 meters per second. As the ball rises through the air, its vertical speed gradually decreases until, at the peak of the trajectory, the ball's vertical speed is 0. Then, as the ball falls back down to the ground, its vertical speed gradually increases until, when the ball hits the ground, its vertical speed is back to 22.1 meters per second. While the vertical velocity is changing, the horizontal velocity stays constant at 47.7 meters per second. The ball leaves the ground with an overall speed of 52.6 meters per second. As the ball rises through the air, its overall speed gradually decreases until at the peak of the trajectory, the overall speed is 47.7 meters per second. Then, as the ball falls back down to the ground, its overall speed gradually increases until, when the ball hits the ground, its overall speed is back to 52.6 meters per second. To improve your intuition for how velocity and speed behave during projectile motion, I suggest that you pause the video and study this sketch. Now let's ask whether our results make sense. Remember that a meter is roughly 1 yard, and remember that a football field is 100 yards long. The problem told us that the ball traveled a total horizontal distance of 215 meters, which is about 215 yards, or about 2 football fields. That's a reasonable driving distance for a golfer. We found that it takes the ball about 4.5 seconds to travel that distance. That's a reasonable hang time for a golf drive. The problem tells us that the ball reaches a height of 25 meters, which is about 25 yards, 1/4 of a football field. We found that the ball was hit with an initial speed of 52.6 meters per second. 1 meter per second is roughly 2 miles per hour, so the ball was hit with an initial speed of about 100 miles per hour. That means that the club head was moving at about 100 miles per hour when it hit the ball. That's a reasonable club head speed for a golfer hitting a drive. Now let's do a recap of our work on this problem. In projectile motion, the vertical velocity at the peak of the trajectory is 0. So we were able to substitute 0 for v sub y at time 1. Because we know the vertical velocity at t sub 1, but we don't know the vertical velocity at t sub 2, we chose to use t sub 1, not t sub 2, as the final point that we will plug into our kinematics equation. Don't assume that you should always choose initial and final points that are located at the beginning and end of the projectile motion path. This is the first video in this series in which we've used this kinematics equation. At this point in our solution, we needed to use either an equation that was missing delta t, or an equation that was missing v initial y. We chose this equation because it's missing delta t. We used the components of the velocity at time 0 to find the magnitude and direction of the overall velocity vector at time 0. We used the Pythagorean theorem to find the magnitude of the velocity. The problem also asks for the direction of the velocity vector. The direction of the overall velocity vector can be described by an angle. We used a SOHCAHTOA equation to find the angle formed by the velocity vector. To solve this equation, we had to use the inverse tangent function. Projectile motion is symmetric, so the horizontal distance that the ball travels as it rises from the ground to the peak is equal to the horizontal distance that the ball travels as it falls from the peak back down to the ground. And the time it takes the ball to rise from the ground to the peak is equal to the time it takes for the ball to fall from the peak back down to the ground. So, we were able to calculate that this distance was half of this distance. And we were able to calculate that this time elapsed was double this time elapsed. In projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. We found that the ball's horizontal velocity is positive 47.7 meters per second. This value applies at every point along the trajectory, so we use the same symbol, v sub x, for the horizontal velocity at every point along the trajectory. We found that the ball's vertical velocity at t sub 0 is positive 22.1 meters per second. So the ball's vertical velocity changes from positive 22.1 meters per second at t sub 0 to 0 at t sub 1, and then finally to negative 22.1 meters per second at t sub 2. So we use three different symbols for the vertical velocity at t sub 0, for the vertical velocity at t sub 1, and for the vertical velocity at t sub 2. To succeed in physics, think in terms of components. The ball's horizontal speed is constant, so to find the point with the smallest overall speed, we had to find the point with the smallest vertical speed. For a projectile motion problem, build as much kinematics information as possible into your sketch, as we've shown here. Build all the information provided in the problem into your sketch. And whenever you figure out new information, build that new information into the sketch. When possible, build the question into the sketch, like this, or like this. Building the question into the sketch will help you to avoid the trap of saying that the answer to part B is 2.255 seconds. Draw a large sketch so that you'll have ample room to include all the relevant information in your sketch. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.